Yeah, I'm Jim Jiao in the Department of Applied Mathematics and Statistics. So I'll be talking about variational methods and algorithms, but it sounds boring, so I changed the title to be Fighting Crimes and Breaking Barriers. And the crime we are fighting are variational crimes in mathematics, and barriers we are breaking are basically doing the impossible that some theorem has said that this is upper bound you can get, but we are trying to break over that by showing that the theorem was actually wrong. So in my research group, we work on basically the three circles of computational science that Robert showed. And my students are working on the fun things, developing algorithm and codes for solving linear algebra problems, getting optimal time complexity using multigrid methods, and try to do the holy grail of linear algebra to develop black box solvers that is nearly optimal and robust. And Oliver and Jiao are working on these problems, and other students, including Jiao and Oliver, they are working on computational fluid dynamics, multiphysics coupling, climate modeling, doing data exchange across different physics. So when I'm not teaching and not meeting with students, I spend my time thinking about the mathematical foundations of numerical methods for computational science, and in particular for partial differential equations, in terms of what are the optimal conditions, what are the limitations of the most commonly used methods, and are there hybrid methods that you overcome these limitations while maintaining the optimality. So that's basically the overview of the activities of my group. So here is a brief diagram of the history of numerical methods back to like 1700s, starting with Taylor series expansions, and that Brooke Taylor, I think that's the godfather of numerical analysis, because in numerical analysis textbooks, like every other page, you have Taylor series expansions to do the analysis. And well, from there, and nowadays we solve all kinds of challenging problems in computational science, fluid dynamics, solid mechanics, and many methods are based on either finite difference methods for PDEs, which were mostly developed in the 1920s in terms of theoretical foundations, Jiao conditions, equivalent theorem, and so on. And finite volume element methods, those were developed from like in 1950s, 60s, and got really popular in the 1970s. And their theory were mostly developed based on Hilbert space, functional analysis, all those things. And after that time, numerical linear algebra got really powerful, and it unified many of the mathematical. Well, you can use it to analyze many of the theory behind your numerical analysis, except that they are not really compatible with Hilbert space. They have shared roots, and they are also like PDE theory, Green's functions, and so on. So basically, there are different branches of applied mathematics that are the foundations for the numerical methods we're using nowadays. Finite difference mostly based on Taylor series, Green's functions analysis, and finite elements are 99% based on the Hilbert space analysis, and it's incompatible with anything else. Well, pretty much. I cannot say exactly. So anyway, there have been a lot of work done on mathematical foundations, and for finite element methods, 1970s was the golden era, and isn't the mathematical foundation well established? So why am I still think about these problems? Especially think about the successes we already have so far. So finite element method in particular, they're really successful in solving points on equations, heat transfer, linear elasticity, and so on. And in the classic textbook, like Gilbert Strong and George Fix, and citing works by like another guru, Theolet, and it claims that when you use curved boundaries and using isoperimetric elements, if you use degree p finite element, it should converge at p plus first order in L2 norm. And that's in the textbook, that's the classical textbook. And now here is the first grade math question. If you use degree 2 FEM, which means that p is equal to 2, based on this claim, what is the order you should be getting for these two problems on solving this Poisson equation on these two domains with curved boundaries? One has concave boundary, one has convex boundary. It's first grade math question. So it's p plus 1, that's 3. Okay, any other guess?
How accurately can you represent your boundary?
The boundary is represented using as parametric elements, which is using quadratic to represent it, and the theory says it should be third order accurate. And well, if you look at some analysis, they claim that well, convex, concave will make a difference and so on. But here's the thing: this curve is for the quadratic elements. It's second order convergence rate. For concave and convex domains, it does not matter whether it's convex or concave. And the theory, the classical textbook and the classical analysis were incorrect. It's second order, not third order accurate. So Matt mentioned that they have this problem that they cannot derive something. Now we have textbooks that were like 50 years and it's incorrect. I don't know which one is worse. Basically, what has gone wrong? Well, what has gone wrong is that there are some implicit assumptions used in the classical analysis. I'm not going into details, which basically it has some implicit assumptions about continuity of the functions so that you can apply the theorems from function analysis. But the assumption is broken when you have discontinuous monodirections. And this assumption, well, it's hidden and it was not analyzed because of the what is so-called variational crime. That's why I said fighting crimes. So recently, if you work on PDE, you probably have heard of isogeometric analysis. It's really, really popular with at least thousands of followers developed by Tom Hills, and it was developed to overcome these convergence issues without, well, there was no analysis. Basically, they found that this works, but exact geometry is only a sufficient condition, not a necessary condition, and it makes mesh generation extremely complicated. So understanding the root cause of the problem will make our lives much simpler in terms of better algorithms, faster, simpler. And here another slide. Is the mathematical foundation really established already? Well, here is another quote from the textbook that the optimal convergence rate when you have degree p is p plus first order. So there was this is optimal bound. You should get this on the previous picture, and on this picture, well, this is the best you can get. And there are also constraints about the angle conditions for the meshes for finite methods, maximum angle, minimum angle, and they have been used for decades and decades for all the researchers developing methods and generating meshes. So here is a question for you. Between these two meshes, these are quadratic meshes, which one is better? Which one will give you better accuracy? Looks like the left one gives you better angles. Maybe it will give you better accuracy. And or it doesn't matter because p plus 1 is the optimal. Here's a surprise. With the second mesh, which is simple and looks bad from angles, it gives you the fourth order convergence rate and almost 2 order magnitude better accuracy than the left one. So all the people spend all the lifetimes developing like Delaunay triangulation and all those things. Well, sorry, the theory was wrong in terms of guidelines. So basically, the classical analysis could not explain why you get fourth order accuracy. And it could not explain why symmetric meshes are better, which means that a lot of optimal methods claimed in the textbook, claimed in the literature, they're actually aiming for suboptimal convergence rate. And so our goal is to develop these truly optimal methods that based on correct mathematical foundation, and it will significantly reduce the computation times and increase the accuracy. Okay, so in summary, I'm just, as I told you, we're trying to develop unified mathematical foundations, and that's what I'm dreaming about every day. And by integrating approximation theory, PDE theory, functional analysis, differential computational geometry, linear algebra, so basically the 300 years of a history in computational and numerical methods, and unify them so that there will no longer be crimes when you combine them together. And why this is important? Because without this understanding, we cannot really develop truly optimal methods, and that's what my group students are focusing on, developing these methods based on sound mathematical foundation. Hopefully I get them right. And finally apply them to computational fluid dynamics, climate modeling, and some students have the posters outside on methods for climate modeling for conjugated heat transfer. And that's it. Exact on time.
Jim, thanks very much.
Thank you.
Questions? I know there's lots of people using meshes and grids in the audience.
I have a question.
Yeah.
In your last but one picture, you demonstrated that the irregular mesh is better than the regular one.
Actually, this one is better than this one.
Which one?
This one is
The
better.
symmetric one.
Yeah.
Okay.
Yeah.
My question was if you can easily have an adaptive mesh. Sometimes in solid state theory we need adaptive meshes.
Yes, you can. So that requires a very solid theoretical analysis to generalize this. I call this uniform, or it satisfies some centroidality property like Voronoi diagram. And there is a quasi-centroidality so that you can distort it slightly and you still get this superconvergence. And that's, that's very complicated. Yeah.
So, I have a similar question actually about this. So, I have been using both irregular and regular meshes, and I know that everything is very nice with the regular meshes unless you have irregular boundaries.
Mm-hmm.
Once you have irregular boundaries, you have to go to regular mesh. And then
Mm-hmm.
the question is whether you want to connect really irregular and regular mesh.
Yeah.
Because then you can get problems on.
That's
on
right.
the points.
So
Yeah.
this is this point here. The finite element method is confined by the functional analysis, and it cannot break out of functional analysis. So to do this, you really have to have generalized variational formulation that you break out functional analysis in your boundaries. So near boundaries is a nonlinear problem, and functional analysis treats it as a linear problem. The theory is incorrect. That's basically why with curved boundaries you lost this convergence. P plus 1 is gone. Reduces to P when you use Steven degree, because that's the functional analysis limiting factor. So the short answer is that you cannot really do that with finite element method itself. You have to use some hybrid method in your boundaries to deal with nonlinear problems. Treat nonlinear problem truly as a nonlinear problem. Yeah.
Jim, thanks very much.